have a camera that is not calibrated and we want to calibrate that camera. Calibrate a camera is like saying that we want to find the parameters of the camera, intrinsic and extrinsic parameters. Okay, the situation is this one. We have a point in the real world, P, that has coordinates. Okay, we can call it x, y, and z. Okay, for simplifying, we can say that the coordinates are x vector, big X vector. Okay, this is big X vector. Then we have I will rapidly draw this. We have just a coordinate system here, and here there is the image plane. Okay, the plane in which we want to project P. So this is the projection. But working in this with these settings here is not easy because we will have like all the values with different sign. So it's easier to just suppose that the coordinate system is inverted to the with the image plane. So let's be clear. Here we have a real point. Here there is the theoretical coordinate system of the camera. Okay, we are projecting and the image plane is behind, but is inconvenient from a computational mathematical point of view. So we will delete all of these settings here. Okay, I have deleted what I've drawn. Now, so we can suppose that here we have the camera coordinate system. Let me draw it better. Okay, this is the camera coordinate system. We have the x-axis, z and y. Cam coordinate system. And here there is yes, here there is the image plane. This is like a theoretical plane. We cannot see it. Okay, this is a real point. We can see it. We can like put an object there. But the plane here is just a theoretical plane, the image plane. We will now project the point P in the coordinate system of the camera. Okay, very good line. This is the intersection between this line and the image plane. It's called P prime. Okay. Now, the geometry that control this type of system, it's called pinhole geometry. P pinhole geometry. And it's the geometry that control basically it's the geometry that works inside the inside the first cameras. Now cameras are more complex, but basically we can say as an abstraction that this is the geometry of the camera. Okay, in this type of geometry, when where we are projecting in this way, it's the same geometry that we use when we use our visual system. Okay, here we have the eyes, and we project in the brain coordinate system. Okay, um, so a point p prime has its own coordinate, uh, but he is in a plane. It's in a plane, not in 3D. So he has just x and y. Okay. We can say that x and y, it's a vector, the vector x, small x. Now, from the pinhole geometry, we know that x is equal to f multiplied by big X divided by z, and small y is equal to f multiplied by big Y divided by z, where f is the focal distance. The focal distance is the distance between the coordinate system here and the image plane. Okay, f. F, like the image plane, it's a theoretical distance. It exists, but it's just theoretical. We can estimate it. We cannot measure it. Okay. So saying that x is equal, small x is equal to f multiplied by big X divided by z is like saying that z x is equal to fx and zy is equal to fy. Okay. Now, um, we can pass from the coordinate that we have seen to homogeneous coordinates. We are just adding a 1. Okay. So x becomes x vector x big becomes x y z 1, and small x vector becomes small x small y 1. Okay. Now I want to repeat a thing. We don't have z in the small x vector because we are projecting in a plane. We are losing z, and this is not a case. We are losing z because z is the depth. We cannot understand depth looking to an image. Okay, we can understand depth looking to an image just because we are human. We have lived a life, so we know that, for example, if there are mountains in an image and they are small, they are smaller than a person, probably that mountains are very far. Okay, but we know that just because we are humans and we know the world. An alien without knowing knowledge of the real world cannot understand image and depth using image. So we are losing z basically. Now all the formula here can be rewrite in a matricial form. Okay, so we can say that um, okay, I will use another notation. I will use this. This is this vector, okay? X multiplied by z, y multiplied by z, and z. It's basically this multiplied by z. And it's useful because we want to use this, okay? So, in a matricial form, we want to find xz, small xz. This is a vector with three entries, and we want to obtain it with matricial multiplication, okay, a product between matrices and the vector x. Okay, let's be more precise. I will put here directly the coordinates, so x, y, z, 1, homogeneous coordinates. Now, how can we pass from this to this? We have the formula here from the pinhole geometry. Oh no, we know that we just have to we want to find this, and these are x and y multiplied by f. Okay, just that. And also we don't need z, so we have to delete a coordinate. So multiplication for f, product for with f, and deleting one coordinate. Okay, nothing more. For deleting a coordinate, it's easy. We just need a matrix like this: 1 0 0 0 0 1 0 0 0 0 1 0 stop. This is, we can call it P0. Okay, this is a projection matrix. This is just a matrix that delete Z. Just that. And here we can put just now applying first of all this matrix multiplication. Okay, think about that. We can multiply first of all these two matrices here and delete Z basically. Then it will become a 3 entries vector. So now we have a 3 entries vector, and so we can multiply a 3 by 3 matrix for a 3 entries vector. So f0 0 0 f 0 0 0 1. Or you can first of all do this product and then multiply to the vector here, but it's the same. I prefer to think about it as before deleting z and then multiply by f. Okay, so this is the calculus, just that. What's the problem? There are a lot of problems. First of all, when we project in this way, the point here that we are obtaining, let's redraw here. We are projecting here. There is the image plane. There is the image plane. There is a point here. We are projecting. What's the problem is that what we are finding is p prime, and p prime as scenario here. We are supposing that p prime is the origin of the image plane. Okay, it's like 0 0. If we don't add anything here, we are supposing that p prime is the origin of the image plane. Okay, but this is a problem because usually when we deal with image, the origin is here. Okay, it's here, and the two axes are here, x and y. So we have to move the origin from here to here. Okay, from the principal point, this point here is called principal point, from the principal point to the real origin of the image. How can we move this point from here to here? Just adding, just changing the coordinate from 0 0 to px py, where px and py are the coordinate of the principal point, supposing that the origin is here. Okay, it's not difficult. Okay, it's not difficult. It's 0 0, but we want to think about that like px py, just that, because the real 0 0 is here. How can we do that? We can just change a little bit this formula. Okay, because now we don't want, let's have a look to the formula written before. We have zx equal fx and zy equal fy. Let's rewrite it here. Z, big Z, x equal f x and z y equal f y, and this give us the principal point in 0 0. We want to add, just to add px and py. Okay, sorry, I did a little mistake, a small mistake. I was saying, sorry, I did a small mistake. I deleted. I was saying that we want to change the coordinates in this way. We know that this is true, okay? Let's come back to the other notation with without z. So x is equal to fx divided by z, and y is equal to fy divided by z. We have to add, as I said, px and py. Okay, just that. So looking at the matricial form, for adding px and py, we just can modify the matrix, inserting px here, px, and py here. Okay, so now we are adjusting the formula. Okay, now there is another problem. There is the fact that maybe it's possible that inside the image plane, in the camera system, x and y coordinate are not orthogonal. Okay, if they are not orthogonal, we need a parameter that control the skewness. Okay, a skew parameter, the skewness parameter, and we can put it here. Okay, it's called s. So okay, so let me I need this. Okay, let's put it here. We have s. Okay, so this is the situation. We can say that this matrix, we can call it kf. Okay, we just have another problem, the last problem. The transformation that we are doing, it works, but it's in meters. We are dealing with meters, but we want to, but here we are in a pixel world. Okay, so we have to modify the unit measure, passing from meters to pixels. How can we do that? Let's take kf. Let's take kf. Let me write it here. It was f s px 0 fpy 0 0 1. This is kf. We and it's in meter. Okay, we will multiply it to the left, in the left, by the matrix ks. There is a matrix in pixel over meter for changing the unit measure. Okay, this pixel is just a converting matrix mx 0 0 0 my 0 0 0 1. Okay, doing this product, we will obtain fx sx, and then we can just change the notation because we now have these two translation, this translation here, but in another unit measure. So we can say that px now is u0 and py is v0. So fx sx u0 0 fy v0 0 0 1. And we can say that this, finally, it's in pixel and it's called K. Without S, without F. This is the real K, okay? And it's in pixel. Pix, not px, pix. Pixels. Pixels. Okay? So this is the matrix that we want to use. So now we have the complete transformation, not complete, but we are very near. We are saying that x is equal to 1 over z that multiply the matrix f of x, s of x, y0. I remembered you that this is not necessary. We have to put it just if the two axes of the camera system are not orthogonal. Then 0 f of y v0 0 0 1. This is k, and we multiply it by the matrix P0, that is 1 0 0 0 0 1 0 0 0 0 1 0 P0, okay, and then multiply by let me write it like this. We multiply it, no, multiply it by, sorry, by x, like this. Okay, we can change the notation and say that this k multiplied by p0 is p, just p. And so, another time, we will rewrite everything. X is equal to p, no, sorry, 1 over z multiplied by p multiplied by x. Okay, okay. It's not complete. Why it's not complete? Because from the start, from the beginning, we are dealing with point and projection, but we are just adjusting the coordinate. And why we are adjusting the coordinate? We are adjusting the coordinate because in the real world, when we pass from the real world to the camera system, we have to change the unit measure, and it's what we are doing with k, okay? We are changing the unit measure. We are also passing from the origin, the principal point, to the origin of the real in the edges, okay, the origin in, sorry, in the corner. So we are translating, we are deleting one dimension, okay, but what we are really doing is scaling, and we need to scale because objects in real world are not represented in the same way when we look at it in a camera, okay? We are like distorting it a little bit. Things are different from the real world and the camera, okay? But we are not now considering the fact that camera and real world are not aligned, okay? We are just dealing with the fact that a very huge world here is represented in a display. We, for now, for 20 minutes, for 30 minutes, we have just see how to represent a huge world inside a small display. But we have not deal with the fact that when we use a camera, we can use it from a lot of different perspectives, okay? We can rotate it, we can roto-translate it, and always we do that, okay? If we take a photo of the same object from different perspectives, it will be different. So now we have to deal with this. So now the x, big X, that I always have called big X, I will start to call it X cam, okay? Because usually in all my because in the entire video I was speaking about X cam, about the coordinate system of the camera. Now we want to deal with the real X of the point in at the beginning. I didn't start from that because it's easier in this way. That is X word, okay? X word. Okay. So now we can use the same equation as before, okay? But we have to pass from the x word to the x cam, okay? We just have to find this function here. How can pass from x word to x cam? We just need a roto translation, okay? Because in the Euclidean space, for passing from a point from a I don't know, for roto translate things, okay, we just need a, a matrix composed by a rotation and a translation, okay. We just need that, so we are searching to this a roto translation matrix, okay. In our case the rotation is 3 by 3 and the translation is 3 by 1, so the matrix is 3 by 4, okay. This is a 3 by 4 matrix. Okay, but we can basically the role of this matrix here p0 is just to delete a coordinate, okay. So we can encode this function here, we can encode it inside the roto translation matrix, okay, putting just 0, and so we can rewrite everything, and we will obtain that x cam is equal to 1 over z. Let's see here, okay. We have p. What is p? P is written here. P is k multiplied by p0, okay. Then multiply by this that I told you is x cam and not x word, okay. So we have k, then we have p0, then we have xcam, but xcam in reality we can obtain it roto translating the x word, so multiply by rt multiply by xcam, okay. But we can encode this inside the roto translation matrix, okay. So let me delete this matrix here, okay. And so we just remain with this equation here, okay. This is our equation, and we can call this matrix, this is very important, this is the k matrix d, and it contains the matrix that the entries of this matrix are called intrinsic parameters, while these entries here are called extrinsic parameters. What does it mean? Intrinsic and extrinsic in English, they means intrinsic is like something that is inside a thing, okay, and extrinsic is like outside, basically. Why is that? Because it's what I told you before, what I said before. K controlled. Let's have a look of K. K is this. K just control the transformation that is inside the camera. This just depend of the camera on the type of camera that you have and the dimension, the model, something like this, okay, and the settings of the camera. So this is just transformation due to the fact that you are passing from a real world to a small object, okay, so intrinsic. These are parameters that control the roto translation that we need for passing from a theoretical world global point of view coordinate system to the coordinate system of the camera in that precise moment, okay. When we calibrate, when we do a calibration, we are supposing that the camera is fixed, is still, okay, is not moving. Okay, so this is the model. This is the model. This is the geometry model. This is what. This is the theory. Okay, this is the theory. How can we calibrate a camera? Because we have speak about things, but we have not understand how to calibrate a camera. Just speak about the geometry. Okay, we can now give a name to all of this. We can say that all of these, so all of the parameters that we need, all of the things that we need are called M. Okay, M. Now, we can find M. How we can find M? Um, Let me write everything in a simpler way. We can let remove this because we don't care about this. Okay, so let multiply by z. We will obtain z multiplied by x cam equal to the M matrix. Okay, the M matrix, we don't know the M matrix. We are searching the M matrix, and everything passed through the M matrix. Okay, so we just have X cam, and we want to find M matrix. So it's we don't know it, so it's M11, M12, and so on and so forth. Okay, we this is a, you can check it. This is a 3 by 4 matrix, 3 by 4. Okay, and we want to search it. We want to find it, but it's not so difficult. Why? Because if we have a fixed camera in a point, okay, I will try to draw it. We have a fixed camera here. No, 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 no. We have a fixed camera here like this. Okay, we have a camera here. Too complex. Okay, we have a camera, and the camera is watching the, like here there is the display. Okay, here I will let's suppose that someone look in this direction. Okay, the display that he sees is this one. Okay, and the camera look to a like a, I don't know, like to different object, like a ball here, and I don't know, a ball and a, I really don't know, an umbrella. No, I don't know what to draw. I don't know the name in English of the things, but let's say something like this. Okay, like this. Okay, I don't know. Uh, the display will show us something like this. Okay, so what we have to do, this is fixed, look, it's very fixed, it's still uh, we know the exact position of this because it's in the real world. We can touch it. Okay, we can touch it, so we know, for example, these 2 points, we know the coordinates, and we know the point, the correspondences. We know the point here in the display, we know it, okay? So we know that this real point is connected to this real point, and the same for this, okay? We know it, we know it exactly. So we can collect a set of point correspondences. We can exactly do what I'm drawing here. This is not an example. This is exactly what people do. Okay? So take a photo of object with a still camera and then connect the point in the real world with the point in the image. Okay? So we will obtain, let for example, suppose that we have one correspondences, okay? For example, this one. So one point in the image and one point in the real world. Now we can say that x, now we have everything, okay? No, not everything. We have the coordinate. We know that xz multiplied by yz divide no, sorry, not multiply, these are different entries. This is equal to this is the matrix M. I don't want to write all the entries here. This is matrix M multiply by x, y, z, 1. And now we know it. We know this and this. So this is setting a linear system solvable. Okay? Let's look at it. Now I will do some steps in mathematics, very boring. Okay, so let's put to faster the video. We know now that xz is equal to m1 1x plus m1 2y plus m1 3z plus m1 4. Okay, then we know that y, z are equal to m2 1x plus m2 2y plus m2 3z plus m2 4, and z is equal to m3 1x plus m3 2y plus m3 3z plus m3 4. Okay, so we can plug the last equation inside the first two, okay, and obtaining this is big. I will try to write in a smaller way. Okay, so m3 1 x plus m3 2 small x big y plus m3 3 small x big z plus m3 4 small x is equal to, no, I cannot write it here, so m1 1 x plus m1 2 y plus m1 3 z plus m1 4. I don't want to write it, it's too long, but the same, okay, the same. I have just, this is the result of plugging z in the first equation, then we can plug z in the second equation and obtain another equation, okay? Now we can rewrite the two equations that we have here, the first one and the second one that I don't want to write because it's long. We can leave the zero alone and put everything to the right, okay, and this allow us to write this equation here in a matricial form. Okay, so let's keep it to the matricial form. This is the matricial form. We have something like, let's call it A. This is the matrix A. We have like x1. Okay, I'm writing 1. Okay, no, x, just x. X, y, z, 1, 0, 0, 0, 0, minus x, y, no, x, x, minus x, y, minus x, z, minus x. All of these are multiplied by this column vector m11, m12, m13, from here to m33. No, not 33, I don't remember, m34, 34. So m has 3 by 4, 12 entries, and here we have 12 entries. Okay, this is a matrix with 12 columns, and this is a vector with 12 rows. Now, what I have to put here, you can check the what I have wrote here if you don't trust me, okay? But I did it one time and I know that is right. I have to plug here the equation that we can find with other points, okay? So this, what I've wrote here, is just related to the first point. So we can change the name here and say that these first 3 are the coordinates of the first point that I've taken. Okay, so this here, and this 1, 1, 1, 1, 1, 1, 1, and this small x is the first coordinate of the point, but in the display. Okay, so this x is the coordinate of this point in the display. I just forgot to write the second equation. Here we can put a very similar equation, but with 0 here, and x1, y1, z1, 1, minus y1, x1, minus y1, y1, minus y1, z1, minus y1. Okay, then we have to, we have to put other points here. Okay, lot of other points, point correspondences from 1 to n. Okay, so basically we will have the same 2 rows here, but with xn, yn, and so on. Okay, for example, xn, yn can be the coordinate of this point in the real world. Okay, so we will obtain this linear system that can be rewrite as something like ah equals 0. Okay, this is what I have to solve now. Okay, it's clear. We have find correspondences between real world point and digital image point. We can do that. Okay, we can do that. And just rewriting everything in a simpler way, we will obtain AH, where H are unknown and A are known. Okay, so we want to find H. H is composed by 12 points, and as we have said here, with one point give us 2 equations. Okay, so Since we have to find 12 entries, we need at least at least 6 points. 6 points correspondences. So I mean six correspondences. So 1, 2, 3, 4, 5, 6. Okay. So 6 points in display and 6 points in the real world. Okay. Now the matrix A that we will find can be of can be we have to check the rank of the matrix. Okay, rank of A. If rank of A, if it's smaller than 11, something wrong happen. Okay, it's we cannot okay, something wrong happen. Probably we have taken coplanar points. Okay, and this is not good. It's not good just because if we take coplanar points, we are losing information. We have to take points as different as possible. Okay, so otherwise rank of A will be exactly 11. Okay, and being rank 11, um, he has the matrix A 11 degrees of freedom, and as I said, with 6 points we can find a solution. Okay, how can we find a solution of a linear system like that? Using a method that you can find online. Okay, that is called SVD decomposition. Okay, so we take A, we do SVD decomposition, and then take the eigenvector with smallest eigenvalue. But this is just a method for solving linear system. What it's really important is what we have said before. Okay, that this is the model. We want to find m. We can find m building a linear system, and then for solving it we use this SVD decomposition. Okay. Now we have find m, but is this useful? Not much. No, yeah, it's very useful, but if we stop here, it's not useful. We need the intrinsic and extrinsic parameters, because I told you m is composed by k multiplied by rt. Okay, intrinsic and extrinsic, and we need each of them, not their product. It's like saying that we have find 6, but we don't. No, not 6. I don't know. It's like saying that we have find. It's like saying that we have find 6, but what is 6? Is 1 by 6 or is 2 by 3? We need to know this, okay? It's important. So we have to factorize m, and for factorize m, there is factorization is just this process here. Find matrix that compose other matrix. We will use the RQ factorization. That is another method like SVD decomposition that you can study online. Okay, it's just a method. With RQ factorization, we can factor. RQ is just a name. Okay, R, it doesn't mean anything. It's not related with this R. Okay. In RQ factorization, R is upper triangular matrix, is an upper triangular matrix, and in our case is K, while Q is an orthogonal basis, and it's in our case R. Okay. The last column that we need, T, is T is the inverse of K. So K, the inverse of K multiplied by last column of M. Okay. Is the inverse multiplied by the last column of M. Okay, this is the method. So just RQ factorization. Okay, so now we have find K and R and T, and these are what are searching. Okay, so we have done. So we are done. What we need. Okay, there is a little thing that I want to add. Finding M in this way is just without physical meaning. Okay, we are just putting points in a way, points to the left, to the right, and solve a linear system. Okay, but this is just a method that can work for every situation in the world. Okay, it's not a specific method for camera calibration. It's just a mathematical method that allow us to solve linear system. But this matrix here has a role, has a meaning, has a physical meaning. This is a rotational matrix, this is a translation, and this has some meaning. Okay, so we are not using that meaning. We can create a more robust algorithm, okay, in which, using what we have seen before, so we can estimate M as we have seen before. Then we can reproject points on the on the image plane. And what does it mean? It means take X, take M, multiply M by X, find X, and compare and look where they are. Okay, reproject. Then 3, we can minimize. I don't want to write all the formula because it's huge, but we want to minimize, so find the minimum of like a distance. Okay, find the minimum of a distance between the X that we have find now, this X here, and the real X in the display. Okay, I will call it real X. Okay, real in the image plane. Okay, squared. We can try to minimize this reprojection error. This is an error. Okay, this is the error that we are committing. We can minimize it using changing the parameters of R, of T, and all the others. Okay, and all the matrix K. Then we can finally ensure, this is the crucial point, that R is a rotation matrix, because rotation matrix has properties that I don't remember. If I remember well, the column are unit vector, then they are orthogonal, okay, and they has to remain orthogonal and with column vector. If you come to the fourth point and R is not orthogonal, something is wrong, okay. So you have to pass, if this is, if not okay, iterate the process, okay. When finally R works, okay, we have finally find M and factorize it in the right way, okay. This is camera calibration. When we have find, so basically calibration is the process of finding K, R and T, and this is the method.